Hello. Welcome back. One more lecture on trees. Today we do threaded binary tree and binary search tree. In threaded binary tree, we will intend to cover everything around why we need a threaded binary tree, and similarly, the likewise for the binary search tree also the same concepts we'll try to cover why we need it and what are the common operations. So we are tracking a syllabus which is on the screen right now, where we are attempting to complete threaded binary tree and binary search tree in today's lecture. Typically, this should be a smaller lecture as compared to the other lectures that you see on this playlist. Typically, we should be able to finish it off within 1.5 hours is what my guess is. Let's understand what we have in store. We would be doing the threaded binary tree definitions, the uses of it, the types of it, the creation of it, and likewise what are the operations possible. Similarly, for binary search tree also the same set of things we will complete, and after that we will complete the common use cases in terms of the commonly asked questions. Now, to start off with a threaded binary tree, let's understand from a binary tree concept what are the problems and hence why do we need a threaded binary tree. We'll try to establish the need of a threaded binary tree from there. So let us say that we have a tree which is represented, each of the nodes of the tree, and I'm sure you know what are nodes, what is an edge, etc., from the last lecture. So each of the nodes of the tree is represented by a double linked list, right? So, and then let us say that this is that double linked list. Now we have let's say B here, and we have B here, which is this node, and we have C here, which is this node, and then we can have one more set of nodes here, which will look like this, and one more set of nodes here, which will look like this. So this will be our let's try to name things on the left side first before we complete the right side. So this is how it will look. So the right side we will have let's say ABCDE, yes, and let's put a right node to this just to bring in some randomness, right? So this is our target tree which we will use just to explain you things. ABCDEF. Now this left pointer will be pointing to the left child. The right pointer will be pointing to the right child. The left pointer will be pointing to the left child. Right pointer will be pointing to the right child. Left pointer, there is nothing. Right pointer will point to the right child. So this is our tree, and we are using double linked list for this tree. Now, if we are actually using this double linked list for this tree, what is the problem in actually doing an in-order traversal of this binary tree? To do an in-order traversal, and please refer to my last lecture for that, we need a stack for that. And when we need a stack, we are 100% sure that we would definitely need to visit the stack in a recursive manner. And when we talk about recursion itself uses a stack, right? From a CPU and kernel standpoint, we would be needing to use a stack to store the program counters, to store the various other memories that we have been using, and roll the stack into a stack winding mode. And when we are done, we will unwind the stack. As we pop out the elements of the stack, we will unwind the stack, and then we will have to get back those memories and use it. So as we understand that recursion itself is very hungry in terms of memory, so when we are using an in-order traversal for a binary tree, since we have to use a stack and recursion on it, we have to assume that there will be a large amount of cost in terms of both time and space. So that is the first problem from an in-order binary tree traversal standpoint. So the solution to that is don't use a stack. Then how do we get the in-order traversal of a binary tree? And that's the problem that TBT will solve. That is, the threaded binary tree will solve. So that is problem number one. Our problem number two is that if you see here, then there are some pointers which are wasted. For example, this pointer is never used, this left pointer. As I said, we are using a double linked list. We'll have a prev pointer and a next pointer. So the prev pointer here is not used. The next pointer here is not used. Prev pointer not used. Next pointer not used. Prev pointer not used. Prev pointer not used. Next pointer not used. So these are the unused pointers. right? So if you have a tree of total number of nodes as n, and in our case n is 1 2 3 4 5 6, then the total number of pointers that you are actually using, left right for each node, will be 2n, which is in our case will be 12. Now, how many of these pointers are really getting used? That's basically equal to the total number of edges. So if n is equal to 6, we know from our last lecture, total number of edges is n minus 1. So in our case, this would be equal to 5. So if you see the chart, you will see that 5 pointers are getting used. Here, the left pointer is getting used. This is the left pointer getting used, right? Because it is pointing to a valid child. Here, the left pointer is getting used. So this is the second left pointer. Or the second pointer getting used. Here the right pointer is getting used, that is the next pointer is getting used. Here the right pointer is getting used, that is the next pointer getting used, which is the fourth pointer getting used. And here also the right pointer is getting used, which is the fifth pointer that is getting used for us, right? So these are the pointers that are getting used. So I'll just remove them from the chart just so that we can make use of that space later on. So as I established that there are 5 pointers that are getting used, and we have established this number, that how to get this, we'll take the total number of edges minus 1, total number of edges, which is n minus 1, and that's the total number of pointers getting used. Then total number of wasted pointers are how many? So total number of wasted pointers are, we had 12 pointers, right? So 12 pointers minus the used pointers, and we get 7 as the wasted pointers, and that's a large number, right? So we have the wasted 7 pointers, and to generalize this equation, we can say that total number of pointers, which is 2n, is equal to the total number of used pointers, which is n minus 1, and the total number of wasted pointers, right? So the total number of wasted pointers, let us say, is x, right? So we will actually get 2n minus n minus 1 as our x, which implies that our x is equal to n plus 1. So this is the formula of the total number of wasted pointers, right? So if we have a tree with 6 edges or 6 nodes, total number of wasted pointers is 6 plus 1, 7, and that's what we had found out here. So this is how typically you will go do any kind of arithmetic if given a large number, but we are not trying to establish that point. This is a mathematical situation which we are now aware of in terms of formulas. What we wanted to make sure that you understand is that this problem is understandable, where we are saying that the pointer is there but it is wasted, and the number of pointers that are wasted are sufficiently large, and they are coming from your child nodes, they are coming from your nodes which have a single child, and so on and so forth. So that's something that binary tree will have an inherent problem. So we need to have a threaded binary tree that actually solves that problem. So to do that, let us understand now, let us get into what is a threaded binary tree. I'll just copy this into our next section so that we use the same example. So just bear with me for 30 seconds. Yeah. Okay, fantastic. So now if I start off this, let me just remove this so that we can use this space. Yes. So now you have this kind of a tree for which we need a threaded binary tree solution. And to do that, first of all, let us try to figure out what is the in-order traversal for this. So if you do this, the in-order traversal of this would be CBD AEF. Yes. So you can do it yourself. I'm not going to go there. We have covered it at length, multiple lectures. So the in-order traversal for this tree is this. Now, how can we create a threaded binary tree where the same in-order traversal will come out without using a stack, right? And these pointers that are now wasted, these 7 pointers that are wasted, will not be wasted, right? So how can we do that also? So that's something that we attempt to solve. Now, if you think about if you are at sea, don't you think that it would be better Suppose you are at C. Don't you think being at C, if I know B, we can directly go to B, or we can directly print B or visit B, and that's the in-order traversal of B. That is, after C we have to print B. So somewhere in B, C, in this C node, somewhere here, right, if we could store B, then we are actually saving on doing a recursive call to it, to a parent, and starting to do an in-order traversal from the parent again, right? So at C, if we know what is the successor and the predecessor, for example, at D, right, do you think that knowing that you see D, before D there is B, so this is the in-order predecessor. So at D, if we know B, it's easier for us to print the in-order traversal of it, right? At D, if we know A, which is the successor of D, then it is easy for us to not go all the way up to A from D to actually tell the in-order sequence from D, right? So what I'm trying to get at, I hope you can understand, but then it will be much more clearer when we start doing things. So let us start to work on this. All we are trying to say is that these wasted pointers, we are going to use them for actually storing the predecessor and the successor of that particular node in case they are empty. So let us now try to figure out what or how do we actually reuse these wasted pointers, so that the second problem that we had seen earlier, which was that there are pointers to the tune of 7 pointers for a node, for a tree with a node of 12 nodes getting wasted. How do we solve that wastage, right? So what we will first do is we will first of all make space for not utilizing these wasted areas. So we will remove these to be saying that these are pointing to null. Now they will start pointing somewhere, right? And as I said, right, if we somehow establish that being at, let's say, C, right, if we can actually know the in-order successor of B, in our case the in-order successor of C is B. So somehow if here I can point it to B, then at being at C I can actually go to B directly, right? I don't, because these two pointers will only point to the child, they don't go up. So from C I cannot go up, but somehow if I can use this pointer to go up to B, which is my in-order successor of B, then I am getting to print the in-order list or in-order sequence using these wasted pointers. And another example is, let's take D, right? The in-order predecessor of D is B. So somehow here, if I can put a pointer to B, right? Somehow if I can put a pointer to B, then I can directly go to B from D to have the in-order predecessor. And likewise, D will have an in-order successor of A. So if somehow here I can put the in-order successor to point to A, then I don't need to go all the way like this. I can directly print A or go to A from here and visit A, right? So that's the beauty of a binary threaded tree or a threaded binary tree. And let's try to build those threads now. So let's say that we are trying to utilize these two areas. So we are trying to utilize this and this, right? So what do we do to the left? To the left, we will say that in the left, we will have, when the left child is null, then we will have a in-order predecessor in the left child. We will point to an in-order predecessor of the left child. So C's left predecessor is nothing, right? There is nothing here, C's predecessor. So let it be null, right? So we will not be able to avoid this wastage. The C's successor, which is B, is what we can point to. So we can utilize the right to actually point to the successor of C, the in-order successor of C. And that's what this says, that if the right child is null, then we can take that right child to point to the in-order successor. So we are utilizing the right child to point to the successor of, in-order successor of this entire tree, which is B in this case. Similarly, D left will go to the in-order predecessor. In-order predecessor of D is B. So this should start pointing here, right? So this should start pointing here. And what do we have for the in-order in-order successor of D? That should be A, right? In-order successor of D is A. So we will start pointing from the right to A so that we can directly go there, right? And then we have E as the predecessor to be used. E's predecessor is A. So let us use that to point to A. And then we have E's successor to be F, right, which anyway it is there and we have it there. But let's talk about as the normal pointer, but let's talk about F. F predecessor is E, right? So then let's use the left pointer to point to the predecessor, and the right pointer doesn't point anywhere. There is no successor. Successor is null, and hence we have to waste that particular pointer. So at least 2 pointers are wasted now as compared to 7 pointers, and that's what the second advantage or the second problem solution TBT comes out with. So it tells you that, okay, start using those wasted pointers to point to the in-order predecessor or in-order successor, as the case may be. What advantage does it bring in terms of in-order traversal? We will cover that, right? But for now, just understand that we have now created some threads. So these are called threads, the dotted lines, and these are called normal pointers. So these are thread pointers and these are normal pointers, right? So that's what this particular example tries to tell you. Now, if we actually take this now, let us now take this diagram and use it for our next explanation. 1 minute. Let us take this. Yeah. So we will take this and use it for our next explanation, which is here, where we talk mostly about what are the types of threaded binary tree and what is the way in which we need to write a threaded binary tree, right? So let's talk about both now. The way in which we are utilizing the wasted pointers, if you see, we are taking both the pointers, right? We are taking pointer here, we are taking the pointer here, and there we are trying to yeah, so sorry for that. Okay, so we are taking our pointers wherever we see our wastage. Let us say that we see our wastage here, then we are taking a pointer, a thread, to actually point to the in-order predecessor. We are seeing a wastage here, we are taking the thread to point to the in-order successor, right? So if we are doing that, then we are actually, for a particular node, we are utilizing both the wastages. In that case, we have something called as a double threaded binary tree. However, if we were using only one of the sides, right? So for whatever reasons, if we are using one of the sides, then we are reaching to something called as a single threaded binary tree, right? So those are the two types of threaded binary trees that are possible. Now, structurally, what do we need to do? Structurally, if you see, then we need to have something like this. Let's say I draw C. Okay, I will draw C here. So I'm trying to draw C, and C would look like this structurally. So C will have a left pointer, right? So which we will call as star left. And let me make this a bit bigger so that we can write the entire variable name. So what we will have is, let's say I'm just blowing up this C, and I'm trying to explain to you how this would look in terms of code, in terms of memory. Okay, so that's what I'm trying to do. So if I say that C is this particular entire example, or C node is this particular blue box, then first of all, I will have the variable left, which is of node type, right? So this is what we have here. So this is a pointer. Next, what do we have is, we have an lThread boolean variable. So we have an lThread boolean variable, which is the left thread. And what do we mean by that and why do we need it is what I will explain now. Then we have the actual data. In our case, this data is C, right? So in our case, this data is C. And then we have the right thread boolean variable. So this is the lThread we talked about. This is the data we talked about. Now we are talking about the right thread boolean variable. So we are talking about rThread. And then we will also talk about the right node, which is the right pointer, right? So these are the variables that are there inside this structure, and this is how the structure looks in memory. So if you see this, then the value of this left thread would be null for C, right? Because this is null. And what is the um, um, left thread for this particular null pointer? I'll come to that. Before that, let us talk about the right thread. The right thread for C is pointing to B. So I would say that it will point to B, right? If B is a pointer variable, I'm assuming, then I'll put the address of B here, right? So right thread will point to B. Now the R thread and left thread, how does the system know that this is a pointer to the successor and not a child? Because if you remember, we can utilize this for a child also. We can, and we must, because in B we will be utilizing this for a child, unlike D where we are utilizing it for a successor. I hope you understand, right? So the system needs to know that whether this is a successor thread or it is a normal thread. I told you, right? We are creating thread pointers or normal, or this is the normal pointer. So this is the thread pointer, this is the normal pointer. Again, this is the thread pointer and this is the normal pointer, right? So here what we have, we are talking C. What does C have? A thread pointer. So then please make the thread variable as true, the R thread variable as true. Through this variable, it will understand whether my right pointer is a thread pointer or a normal pointer, because it sees true, right pointer is a thread pointer, right? And the left pointer anyway is invalid, so it will be nothing. So there is nothing, whether you give true or false, because the left pointer itself is null, there is no use of that particular variable. Now if I take the same for, let's say, let's take an example where we have both, yeah, let's take E for that matter, right? I'm taking the same example for E. So if I take the same example for E and if I draw these blocks, then of course my data block says that I am E. Good. Okay. And the left pointer is a thread. So the left pointer is a thread, means left thread variable will become true. And where does it point to? It points to A. And the right pointer is a normal variable which points to F, right? So it's a normal variable which points to F. So this will be false. So that is how you will represent a particular node with respect to a threaded binary tree. I hope this is amply clear, and this is how you will represent it, or this is how you will initialize the nodes so that you can build a threaded binary tree for that matter, right? So with that, I think we can jump into the main part of the threaded binary tree, which is an example. I think everything will be clear as we go forward here. So what is the total number of, this is a sample tree. What are the total number of nodes in this sample tree? We have 12 nodes, which means that we will have 2n is equal to 24. Edges will be equal to 11. We know that. So the null pointer will be 24 minus 11, right? So 11 actual edges will be used for the actual normal pointers, and 13 will be the null pointers which will never be used. So those 13 pointers has to be reused, right? So that we can actually save on the space. That is the second problem. The first problem was that we have to avoid in-order traversal. We have not seen a solution to that. We will see that now, right? So let us see that now. So the in-order for this particular example is that HDIB, again, I will leave it for you to probably do that. It's very simple to probably do it. We will now try to establish that we will create this tree, then we will do a traversal, and we will find out that we are getting this in-order traversal without using a stack. That is the intent, and that is how we will prove both the problems. First, the problem of these 13 null pointers will go away, which is wasted, and then the problem of using recursion for stack, for in-order traversal will also go away, right? So that also we will see. So let us build the tree step by step. So first things first, we will build the tree like this. So we will have A, right? So we have A here, then we have B here, then we have D here, and then we have E here, let me put those as we go along. D, E. Then we have H here and I here. Right, so those are the things that we have, and let us do the normal pointers. Left pointer pointing to the left child, left pointer pointing to the left child, left pointer pointing to the left child, a right pointer pointing to the right child, left pointer pointing to the left child, and that's it. Right, so that's all that we can point. Yeah, I missed out on this one, right pointer pointing to the right child. In fact, this was the wrong pointer. This E is supposed to be a leaf node, right, as far as this example is considered. So let me check if everything is okay. DB, DHIE, yeah, everything is okay. Now let's build the right side. Right side we have C. Okay, so right side we have C, which has in turn F and G. So we have F and we also have G. And we also have G, right? And then we have from F, G, J and K, and from here we have a right node into L. So if I actually do the right pointer to its child, left pointer to its child, right pointer to its child, left pointer to its child, right pointer to its child, and then a right pointer to its child. So the rest of the nodes which are not having any pointers are wasted. So let us see if we can rectify those wastes by putting the predecessor and the successor. Let's start with H. H predecessor is null, so this will stay wasted. H successor is D, so I will put it to D. Right, so this is my thread that I will use. Then the I predecessor is D, so I predecessor is D, the left child, right? So sorry, the left pointer, and I successor is B, so we will say I successor is B. Okay, what else do we have? We have utilized this. Let's see E now. E, we have B, so B should be the left pointer, and the right we should be pointing to A, right? So we should be pointing to A for the right. And then we have let's see on this side what we have. G. Okay, G has C on the left, and on the right it gets wasted because G has the last sequence in the Inorder. And J on the left has A, so it will go like this to A, right? And J right has a solid line, which means it is a normal pointer. L on the left will have to go to J, predecessor. L on the right will have to go to F, which is the successor, right? So this is how it will go to F. And then K on the left will go to F, so this is K, so K will go to F, and K on the right will go to C, so K on the right will go to C. So we have finished utilizing left and right pointers to reduce wastage, except for the first and the last node, which anyway stays as wastage. So this is how we build the threaded binary tree. So given a tree like this, these are the threads that you will need to draw. So how do we therefore now start utilizing this threaded binary tree to actually do what we were talking about in problem number 1, which is Inorder traversal without using recursion, right? So in order to do that, what we will do is we will say that we have this threaded binary tree that we had just now done, right? And the way to actually do the Inorder traversal is written on the right. Don't worry, it might look overwhelming here. I just kept it so that you can refer to this slide in case you need this, because the drawings might go away. So let me explain that to you now. Now, how do we actually do this Inorder traversal? So we will have two thumb rules. one of the thumb rules is that, let us see, yeah, one of the thumb rules is that we will go to the leftmost node first of all. Starting from A, which is my root, we will go to the leftmost node. So we will make a traversal. We will make a traversal from here to here to here. We'll go left to the leftmost node till we get a null. Right? We got a null. We stop there. When we stop there, we visit that node. That means we will print that node as the inorder sequence. Right? So that's first inorder sequence getting printed. Now we will investigate the right node. The right node of that particular visited node. If there are only two things that the right node can be. The right node can be either a normal thread, or it can be a threaded thread or threaded pointer. So threaded pointer or a normal pointer, right? So in case it is a threaded pointer, so the right node here is a threaded pointer, right? So if it is a threaded pointer, go there, visit the node. Go there, visit the node means I will actually be printing D. Right, so I have done with this particular thing. Now, once I have gone there and visited D, again the step is go to the right node and see whether it is a threaded pointer or a normal pointer. Here I see it is a normal pointer, right? So I will go there and I will start treating this tree as my node. Like the way I took this as a node and I printed, I'll start treating it as my root of a new subtree. The way I started off with this subtree or this tree, and I took this root node and went left. Similarly, when I encounter a normal pointer, I will treat this as my new subtree. So this is my new node. I will go left till I reach a null. Right? So I will go there until I reach a null, and I will start printing whatever is my relevant things that are coming as per the algorithm. So for I, if I now consider this as the subtree, and then because I am already in the left part of it, right? So I don't have any more lefts. Therefore, I will go to the right and see whether it is a threaded pointer or a normal pointer. So I on the right gives me what? Gives me a threaded pointer. So if I on the right gives me a threaded pointer, first of all, I have gone to the left of I, and to the left of I have reached basically a null. Then the only thing that I have to do is I'll have to print I, right? Because I'm visiting I. So the visit of I will have to come out, right? So the visit of I will have to come out, and then I have to go to the right, right? So don't forget that you visit a node and then go to the right. Because your left node is null, you will visit the node and then go to the right. So we will visit the node because the left node there is no further left child, and hence we will print I from here because we are visiting I, and then go to the right and see what is this thread. What is this pointer? Is it a thread? Of course it is a thread. If it is a thread, visit that node. So we will go and visit that node. So we are right now here. Right? So here, when we are here, then we have to investigate whether the right part of this particular node is actually a normal node or a threaded node. So again, we will see this normal node or threaded node. It's a normal node. So then the entire E will be treated as a subtree again. The entire process restarts. Left child, there is nothing. Okay, then visit E. Left child, nothing, then visit E. Right? So then go to the right. Then go to the right and see whether you have a thread or not. If you have a thread, go visit it. If you have a right, if you don't have a thread, then treat it as a subtree, restart the process. Right? So if you have the right is a thread. So if the right is a thread, then all you need to do is go and visit it. So let's visit it. Right? So we visited it. Now, since we visited it, we can now go right. If the right is a thread, you treat this entire thing as a subtree and start the entire process. Right? So we will treat the entire thing as a subtree and start the entire process. So the entire process to treat this as a subtree will take us left till we get a null. No nodes, no child nodes, right? So then we will stop here because we don't have anything beyond this, right? As a left pointer. Then if we stop here, then we can print this. Right? And then we can actually go to the right and check what it is. So the right of this is a thread again. So sorry, it's a normal pointer again. So then treat this as a subtree. Go to the leftmost node. It is the leftmost node, then print this. right? So then print this. So then we will print L, right? And then we have the right pointer investigation. Right pointer will take us to F. Go visit F, right? Take the right pointer of F and see whether it is a normal pointer. Yes, it is a normal pointer. Then start this with a new subtree concept. In the new subtree concept, you have to visit left till you get an empty child, right? So here we get an empty child. So visit that node. So visit that node means K will come here, right? So then the right of K can be taken to see whether it is a threaded pointer or a normal pointer. It is a threaded pointer. If it is a threaded pointer, go visit that node, which is C, and then go to the right of that node, see whether it is a normal pointer or a threaded pointer. It is a normal pointer. So this becomes a subtree with which we will restart the process. So visit till you get a null child. So I am at a null child. So then I will visit G. Right? And then the right child is null, stop the process. So this is how you get your in-order traversal from a threaded binary tree without using a stack, and that's what we were aiming at. So we solved two problems that we had started off with. Problem number one, our pointers are now getting used. Only the left and the right pointer of the leftmost of the starting sequence and the ending sequence are not getting used. Otherwise, problem two is solved. Right? Problem one is of course solved. Right now we saw how to actually draw the in-order expression from a threaded binary tree without actually using a stack. Right? So that's something that we have right now established from a threaded binary tree standpoint. So I hope you can now answer any question from a threaded binary tree. Let's get into the binary search tree concept, which is the second tree we wanted to discuss. Now binary search tree, I had introduced binary search tree in the last lecture. Now for this lecture, let me rephrase what we had said. We said that given any node, all the subtrees of all the nodes, the subtree of that node's left side will be less than, left subtree will be less than the node value, and all the right subtree will be greater than the node value. So that is all that we need to remember. So it's not just about 30 being less than 50. It is also about 20 and 40 being less than 50. That is something that you need to be careful about, right? Similarly for 30, 20 is the left subtree and 20 has to be less than 30. 40 has to be greater than 30. That way we will build a binary search tree. Now because the binary search tree takes care of the population of this tree from a left subtree being less always than the right, and because our in-order says, what does in-order say? In-order says go visit left, which is our left child, then go visit the root, and then go visit the right. That is what in-order says. And because our left is less than the root and the root is greater than the right? So sorry, my root is lesser than the right? Rightmost is my heaviest and the root is in middle and the leftmost is the least heavy. Right? So therefore the in-order traversal is in the proper sequence of numbers. Right? So left will always, if I traverse in order, then left will always be less than the root and root will always be less than the right. And this, if we recursively do, we get a sorted list. So if we do an in-order traversal of a binary search tree, then the beauty of that is we'll get a sorted list in ascending order. Right? So if you have actually created the left subtree as less, right subtree as more, then you will get a sorted order in an in-order binary search tree. That's the most important takeaway that you need to understand from a binary tree standpoint. Now, can we say that binary tree and a BST is the same? We cannot, but we can definitely say that, let's say given 70, 50, 90, 10, right? So given 70, 50, 90, 10, if I take 70, and then the next number is 50. Where do I put 50? If it is a binary search tree, I have to go left, right? So if it is a binary search tree, I'll go left. Then we take 90. If it is greater than 70, then 90 is greater than 70, we'll put it right. Then we'll take 10. 10 is here. 10 is here, right? So this is a binary search tree. Can we write this tree in a different manner? Can we write this like this? 90, 50, 10. We can write this. I don't see any reasons why we cannot write this. But then this is a binary tree. This is not a binary search tree. this, my friend, is a binary search tree, because it follows that the left subtree is always less than the root, and the root is less than the right subtree. That's the basic principle of a binary search tree. But so I cannot say this is a binary tree which is not a binary search tree, because the left is not less than the root, and the root, of course, should be less than the right, which is also not the case here. So this binary tree is not a binary search tree. But this BST is also a binary tree. I cannot deny that this is a binary tree. A binary tree's definition is what? It needs to have 0, 1 or 2 nodes. Everything here satisfies that 0, 1 or 2 nodes. 0, 1 or 2 nodes. That's what is a binary tree. So a BST is a binary tree, but a binary tree is not a BST. So a BST here is a binary tree, but a binary tree is not a BST. Right? So that's what we are explaining here. Now let's talk about the operations that we can do for a binary tree. Now, if we search for a particular element, let's say we are searching for 60, right? So if the key that we are searching for is less than the node where we are, 60 is greater than 50. So if we start from the root, 60 is greater than 50, then go right. Right? 60 is greater than 50, then go right. So we will go right. Now 60 is less than 70, go left. Now 60 is equal to 70, print found, stop. So that is what is the algorithm. Very easy, right? What is the time complexity of this? So see, if you have to search for a node, you know where to go, right? If it is greater, you go right. If it is less, you go left. If it is equal, you print it and come out. That's all you do, right? What is the time complexity? Best case, you were searching for 50, you got 50 at the node itself, or at the root itself. Then your best case is order of 1, right? So you got it at the root. Your worst case will be where that you are searching for 80 or we are searching for 60, and you have to painfully go through all the height of the tree, right? So you are actually going through a worst case of order of n. But then order of n is for a skewed tree. In this particular binary search tree, it is not order of n. Now, if I tell you that my numbers are like this, let's say 50, 60, 70, 80 and 90. If I tell you build a binary search tree with this, what will you do? You will take 50, your 60 has to go here, your 70 has to go here, your 80 has to go here, and your 90 has to go here. What did you create? You created a right skewed tree. Now if you are searching for 90, how many iterations will you take? You will take n iterations. So your time complexity is an order of n in a skewed binary tree. Skewed binary search tree, right? Skewed BST. But if it is a normal tree like this, right, then you will actually encounter an average case time complexity of log base 2 of n. And we have established that many a times that this is basically equal to the height of this particular tree, and height of a particular tree with respect to the total number of nodes is log base 2 of n. And we have established it many a times. Please refer to the previous lectures to understand that. So the average case time complexity for a tree which is not a skewed binary tree will be equal to the height of the binary tree, which is a log base 2 of n. So that's on the searching algorithm for a binary search tree. Now for an insertion, we know how to insert, right? So, and we will repeat this. Let's say 87 we have to insert. Let's repeat this same example. So we will take 87. Next is 36. So we will see that it is less, go to the left, right? Next is 22, 30. So of always remember, you start from the root, check from the root. So where will where will 22 go with respect to this root? Left. Where will it go with respect to this root? Left. So we will put 22 here. Next 15, it will come here. Next we have 87, 15 we did. Then we have 56. 56 will go here. Don't put 56 on this side, because we said we'll start from the root and then go left or right depending on whether it is less or greater. So 56 goes here, then comes 85. 85 is less than 87, but 85 is greater than 36, right? And 85 is greater than 56. So 85 will go here. Then we have 48. So 48 will go on the left side of this. Then we have 91. So 91 definitely is greater than 87. It will come here. Then we have 72. 72 is less than 87. 72 is greater than 36. 72 is greater than 56. 72 is less than 85. So it will go to the left of 85. Right. So 72 will come here. Next we have after 72 we have 6. So 6 is less. So I think 6 will come here. So that is your how to insert into a binary search tree. Algorithm is pretty simple. If the value is less than the node, go to the left and keep on repeating going to that. But you have to always start from the root. Otherwise, this will never be correct. And if the value is greater than right, go to the right. And if you encounter a null, that is where you start the insert. That is the algorithm for this insertion. So if we now talk about deletion of binary search tree, then there are 3 operations on deletion. Those 3 operations, let's see. First is pretty simple, that deleting a leaf node where there is no children. So if we want to delete 80, which is right now a leaf node, then it is as simple as taking away this node and removing it using the free syntax. Right? So we will remove this pointer by taking the right pointer of 70, making it null, and then we will say free this particular node which was pointing to 80. It's as simple as that. So that way our final tree will look like this. So we just delete the pointer and we make that address free. So that's on the delete of the leaf node. Now let's say there is one single child, right? If it has one single child, for example, we want to delete 60, right? So 60 is having a child in 55. So what do you think should happen? If we remove this 60, don't you think 55 should replace it? Right? So that's what we will do. We will make 55 replace that node. And that's what we are doing here. We are having 55 coming up. So all we need to do is this pointer that was pointing from 70 will need to point here, and this one we will free. And if we do these 2 operations, our case 2 is done, which is deletion of a node with one child. Now comes the tricky part where we are trying to delete a particular node which has both children, right? So that's where we will see what kind of logic we have to apply. So the logic is simple, as long as you understand it. We are trying to delete 70. Now 70 has 2 children. So we said that if it has one children, the child will replace, but it has 2 children. Now which child will replace? We don't know, right? So we will say that we will delete 70. That means we will free this particular node, and this pointer which was pointing here will now need to either go here or it needs to either go here, right? So that we are pointing to the actually correct child. There are 2 ways to do it. You can actually take the largest in-order successor or the smallest, largest in-order predecessor or the smallest in-order successor. So let us see what is the smallest in-order successor of 70. So you'll have to take the entire subtree of 70. So let me just remove this for you. So you will have to take the in-order successor of 70. That is, from 70, what is the successor? So successor will come from everything that is part of this subtree of right subtree of 70. So take anything that is on the right of the subtree of 70. So if I expand this example, then let us say we have 50, 30, 70, 60, 80, and anything greater than 70, right? So we should be having anything greater than 80, which means let's put 85. Let us put 75 here, and let us put another value here, which is, let's say, 82, and let us put 90 here. So if I delete 70, so if I am trying to delete 70, then anything to the right subtree of 70, anything to the right subtree of 70, which is the smallest, is what I will need to take and replace my 70 with. So I will free 70. Yes, I will free this. But I will also need to take this 75, which incidentally is the smallest from the right subtree, and I will push this up. So what will it look like? It will look like something like this, right? So this will be our 75. That is what you will have to have as a deleted child or deleted node which had two children. So if you see, is this a binary search tree? Of course it is. 75 is greater than 50, 60 is less than 75, everything to the right of 75 is greater than 75. So we took the smallest right part and we replaced it. Could we do the other way around? Can we take the least part and replace it also on the left side? We can. So let us go to that approach and let us see if we can do that. Right. So let us say that we have to delete this, and we have on the left, we have, let's say 30 will have 20, and then we will have let's say on the right of 30 we will have 35, and to the left of 35 we will have 31, and to the right of 35 we will have, let's say 49. Right. So can I therefore say that if I am taking a left approach, that I will replace it from a 70 standpoint. In fact, I took the wrong route because I was thinking we were deleting 30. We were supposed to delete 70, right? So 70 has 60 as the subtree. So we will expand that 60 subtree to be much more than 60. So let us say that on the left of this we will have 55. Right, so 55 is on the left of this, and then we will have, let's say 62 here. Now we'll keep it, let us take this as 69. Now if I take the left subtree, what is my left subtree? My left subtree is this of 70, the node that we are trying to delete. That is my left subtree. So if my left subtree actually looks like this, then what we are trying to find out is what is my highest node which is a part of this left subtree, right? Because we are talking Inorder predecessor now and not successor. So what we were doing when we were checking the right side, right, then we were taking the entire tree on the right side and trying to find out which is the minimum element, right? That would have given us what? The Inorder successor. But when we are taking the left route and trying to figure out what is the max element here, right, then we are actually going to get what we call as the Inorder predecessor, right? Predecessor. Now those, either the predecessor or the successor, either approach is correct, and we will have to take that node here. So in our case, what is going to happen is we can see that our largest element here is 69. So we will have to take out this link of 69, and here is what we need to put as 69. And then we have a balanced, or rather not a balanced, a binary search tree again, where you have the left nodes of this 69 to be all less than 69, the right nodes to be all greater than 69. Everybody is happy. So either you do a Inorder predecessor or an Inorder successor, and the way to do it I showed you. Take the left subtree. If you take the left, you have to take the max and replace the actual deleted node. If you take the right subtree, you will take the min because you are doing Inorder successor. So that's on the deletion third case. Now construction of a binary search tree in the pre-order mode. Now that we have done many a times. Just one single step is in between. Last lecture, if you watch, then given a pre-order and so last lecture what did we see? That given a pre-order and an in-order list, then we can easily construct. So if these two lists are given, then from these two lists we can easily construct a tree, right? We can easily construct a binary tree from here. How did we do it? We knew pre-order, the first node is the root, and from the in-order we took this root and found the left and the right subtree and accordingly constructed the tree. This was also applicable for the post order part of it also. So if instead of pre-order, post order was given, then we would actually go on this side to search for the root, right? And then we would have come here and searched for the root's left subtree and right subtree and then build a tree. So either post order, pre-order with in order would be given, and we have to construct a binary tree, is what we saw in the last class. Now we are saying that only the pre-order or post order will be given for a binary search tree, right? So if I say that a binary search tree pre-order is given like this: 40, 20, 10, 30, 60, 50, 70. So this is my pre-order. So if this is given, construct a BST. That is the question. How will we do it? We do not even know the in order. So we know that pre-order and in order both are needed to construct a binary tree, and for that matter a binary search tree. But we are only given pre-order. So all we need is in order to fall back on this approach, right? This approach we already know. As long as we know pre-order, in order, post order, in order, we can fall back to this approach and construct the binary tree. We have done it in the last class. Please see that video. Now, but we know only pre-order. So in order, how do we know? For a binary search tree, in order is the sorted sequence. As simple as that. So sort this. Sort this. What will you get? You will get 10, 20, 30, 40, 50, 60. 70. That is your in order, because we sorted it. Now, do you think this is replicating this? So we now know that pre-order, in order, this is the process. So we now have pre-order, in order. So we can redo this process, right? So let us in short see what is the process. Anyway, I have done it earlier, but I'll do it one more time, right? So pre-order is 40, right? This means 40 is my root. Go to in order, ask it for the left child and the right child. So the left child is 10, 20, 30. It cannot tell you exactly, but it will tell you the subtree. So the subtrees are 50, 60, 70, right? So now the left and right both are not known. So take the left, 10, 20, 30, and see what comes first from left to right, pre-order, right? Left to right, which comes first? 20 comes first, right? Out of this list, which comes first? 20 comes first. So 20 is my root, because the first most element in pre-order is the root, right? So take 20 here and ask it for the left and right child. So it gives 10 and 30 as your left and right child. And that satisfies this, right? That 10, 20, 30 will be the left subtree, right? Now do the right subtree, 50, 60, 70. Which comes first from left to right? We have 60 comes first. So write 60 as the root. Write 60 as the root. Go to the left from in order, which is the left subtree, which is going to be 50. And then go to the right of this, which is 70, which is going to be your right child. So now you have constructed the BST for a given pre-order. It was simple. You have given pre-order. It is a BST. So do an in order, which is just the sorting of the pre-order. So that's what is the construction of a binary search tree when we do a pre-order, or when given a pre-order this thing. Now, if you are also given a post-order sequence, it's also going to be the same. Take the post order, convert it into a sorted list in order, right? Because it is a binary search tree, you are very safe, right? You will just need to sort it to get the in order. So that's what this is all about. Now, commonly asked questions, if we actually see what all is asked. What is a threaded binary tree? We have done it. What are its advantages? We know by now. Right? So I'm not going to repeat it. So I have completed threaded binary tree, where we talked about what is it, why is it needed, what are the two advantages. We talked about those. Short notes will be similar to that. In an in-order threaded binary tree, in-order threaded binary tree means it's a double threaded tree, because otherwise you will not get the in-order. In-order threaded binary tree, the right null link is replaced by the address of its in-order successor. Right null link is replaced by in-order successor, and the left null link is replaced by the in-order predecessor. So that is the answer to this question. So let's move on to the next question, which is write an algorithm for inserting an element into a binary search tree with an example. So we are asked to actually insert an element into a binary search tree. We know how to do that. It is asking for an algorithm as well as an example. So let us take the example as let's say we will have 40, 20, 60 10 30. Let's do this. 40 60 40 20 60, and then let's have 10 and 30. Yeah, I think this should be good. Now if we have 40 20 60 10 30, I will take that example, and we want to insert it into a binary tree, a binary search tree. Then our first step, let's write the algorithm. So let us say that we call this as BST underscore insert. And in order to insert, what do we need to insert? We need two things. We need the root from where we should start investigating the insert, and then we need the key, where we say that key is this element that we are inserting, right? All these elements. So that's our key. Now what we will say here is that BST insert is my algorithm. So the first step of BST insert is the first case, right? First case is we have nothing. If root is null, right? So if root is null, then what do? You create a node. You create a node which is this. So you create a node, or rather let me write it as a node here. So we create a node, we will insert the element, the key, in the data, right? Data portion. You saw the structure of the tree earlier. So we will insert 40 here, and we will return this key to the caller. So the next time I get a request for insert, I will get this key, right? So that I know I need to start from here, and it's not a null key, right? So that's the first step. Second step is, let's say we are trying to insert 20. So a 20 is less than 40, so we should go to the left subtree. So if our key is less than what? We will be given what? Root. We have been given, so the first call we were given BST insert. Let's call it as BI in short. So in the first case we were given BI, and then we were given null, and then we were given 40. So we did this step, right? This is the first step that we did. Next we were given BI with not null, but with the address of 40, and we were also given a key of 20, right? So when we were given that, then our key is less than a root.data, right? So our key is less than root.data, because root.data is 40 and we have got 20. So then what do? We will say that my root left, so my root left is going to be a what? We will have to call BST insert again. So my root left, I'm not going to create the node. Creation of node will only happen here when the root is null. So somehow I'll have to go and make the root null, right? The root of the subtree as null, so that it comes back into this portion again and then creates a tree. Don't worry, I'll explain here. So the root left will be equal to BST insert of root left dot key. Sorry, root left and key. So what does this definitely do? When we say BST insert root left, in our case, our root is right now at 40, because we had passed 40's address when we had called this, right? So definitely what is getting called is the root left, which is null, because 40's left is null. Root is at 40, 40's left is null. So null with what? Null with 20 gets called, right? So null with 20, when it gets called, then it enters here again. It enters here again, creates the node, inserts the key, returns the key. Let's do that. So it comes here, then it creates the node, right? So it creates the node like this, which is 20. Then it will create the node and return the key. So it will return this as the key, right? So 20 gets returned where? Into root left. So my root left is here, right? We were here. We had called it from here. This is the call. Inside the call we had gone and we had created this. But this actually means what? This actually means that we are still here, right? So this means that my root left my 40 is left, is equal to what this will return as the root. So my 40 is left, therefore this pointer therefore gets created, right? So it starts pointing to the new node that got created, right? So that is what the first step is. The second step now is that we are supposed to now insert 60. So if we are supposed to insert 60, then it's just the ulta of it. So if my key is greater than root dot data, right? If my key is greater than root dot data, and mind it, we are right now having the root as, because this call has returned, so we are right now having the root as 40. So we are right now having the root as 40, right? So root is greater, if my key is greater than root dot data, then root dot write, it's just the ulta, as I said, root dot write is going to be BST insert of root dot write, and we will pass the key. So we are at 40. So we are saying that so we are at 40, and we are saying that we are calling bi with ampersand 40, and that is the address of 40, and because we are calling this here, right? So we are calling this with the address of 40, which was the previous return, as the root address, and we are also saying that we want to add 60, right? So when this happens, then it comes all the way here and it checks that okay, we are into here, so it wants to call BST insert again. So it will call BST insert again with what? Root dot write. So root dot write is root dot write in this case is null, right? So because the BST insert says that 40's write is null, right? So 40's write is null, right? So BST insert says 40's write is null, and what is my key? My key is 60. So 60 comes here. So this will be called, and if this is called, then this null code will fire again. That is, create the node, fill up the data, right? And return this key to whom? To here. So this is complete and it returns here, right? So returns here means we are at 40 right now. So that return will be the right node of that 40. Root dot write equal to this, right? So that is what we will do there, and then that's how it will go on, right? So if we now take then this is over. Then this is over means we are back to the place where we are saying that we have access to the root node, which is 40. So when we say 10 has to be inserted, then 10 will be inserted through the right of the root node, right? So we are at the root node, remember? So we will say that let's see what is happening here. So when 10 is inserted, then the first thing that we'll be saying is that bi, we will be having null, not null really, we will be having ampersand 40 because we know the root, which is starting from 40, and we want to insert 10. So it will come here, it will see that it has to, it will see what 10 is less than 40. So 10 is less than 40, 10 is less than 40. Then it will say BST insert root left. So it will say BST insert root left. Root left is pointing to 20, right, with 10. That is what it will say. So again BST insert will fire again, and BST insert, when it fires, it will say that I want to insert into the root left, right, because 10 is less than 20. So 10 is less than 20 means it will go to root left. Right now the root is at 20, right, the root of the subtree. So we will say that root of the subtree now needs to go to root left. Now what is root left? Root left is null. For 20 as the root, root left is null. So it says bi null of 10. So as soon as it does bi null of 10, what happens? Null of 10 means that it will come here again. So it will create the node, insert the data, and return the key. So this key that is returned, so it will create the node, insert the data, and return the key to 20. and 20 will say what? 20 will put that code, that key into its left, right? So 20 will put that key into its left. So this is the link that will get built, right? So that way we are done. Now we are back to the root and we are done with 10. Now we have to insert 30, let's say. Then the same thing will happen. First it will say that bi, I am at the root, I want to insert 30, right? Then it will say that 30 is greater than the root dot data, right? So if 30 is greater than the root dot data, or rather 30 is less in our case, 40 we have as the root, so for it is 30 is less, so it will go to the left. So it will go to the left. When it goes to the left, then it says BST insert a root left key. So my root left is actually going to go to 20, right? So we will say bi ampersand 20 30. The next step is that 20, when we are at 20 and we say again BST insert root key, my root now is 20. So if my root dot data 30 is greater than 20, 30 is greater than 20. So if 30 is greater than 20, then my key is actually greater than the root dot data. So I will go to the right? So if 30 is greater than 20, that means this will fire. Then I will say BST insert root right. Root right is what? BST insert root right is null. And I will say the key is 30. So when I say null, then what happens? My this code starts firing. So what will happen here? There will be a new node created. There will be what? 30 here, and then this will be returned to the caller, which will store it in the right of it. So it will store this node to the right of it. The link gets created, and that's how we actually build a binary search tree like this with an algorithm which is recursive in nature. So I hope you have understood this. You can also draw it as a stack. I think that also will be clearer. But this is every time we will be calling till we encounter a leaf node which is having null, and a leaf node whose child is null, and therefore we have the liberty to create a key, and that creation of key will go and return that root node to the caller, and that's how we will maintain the recursive nature of this algorithm. Now insert the following numbers into a binary search tree, draw the resultant tree, and then delete 48, draw the resultant tree. I think this would be easy for us to understand. Binary search tree, we know that, okay, we will take each node 87, 36 is less, okay, then 22 is less, okay, then we have 15 is less than 22, okay, then we have 56 is not greater than 87, 56 is greater than 36, so 56 comes here. 85 is not greater than 87, 85 is greater than 36, 85 is greater than 56, so 85 will go here. Then 48 is greater than less than 87, greater than 36, less than 56, so 48 will go here. Then we have 91, which is greater than 87. Then we have 72, which is less than 87, greater than 36, greater than 56, less than 85, so 72 comes here, and then 6 will go here. So that is your binary search tree for the given problem. I hope this is easy enough for you to understand how we draw it. Just remember that always visit the root to understand which path you take. Don't assume things. Then delete 48. So if 48 is deleted, what is the case? This is how, if you remember, delete had 3 cases. One, we have the if the node is the node is leaf, that is without any child. Second case is if the node has one child, and a third case is if the node has 2 child, right? So what is the case here? We are trying to delete 48, so it is falling under this category. Node is the leaf. Then just do a simple delete. So we will do a simple delete of this node, and we will remove this link. 56 we will make it null. The link of 56 will make it null. Then delete 48, redraw the resulting tree. This is the resulting tree. Then delete 15 and redraw the resulting tree. Now if I delete 15, what is 15 case? One child. So we are right now here in this case. So if we delete one child, what we need to do? We need to push this child here. So we need to re-establish that link. So all we need to do is we will delete this and we will re-establish the link with 6, right? So we will re-establish the link with 6 here. That was there. That's all we will do, and this is our resultant tree after deleting 15. I hope this is something that you can correlate, because we just now did those 3 cases. Write a C function to find the minimum and maximum elements of a binary tree. Okay, now typically you should not be getting such questions because this is an algorithm class and not a class of writing practical examinations. But in case you do get such questions, then we have to be prepared, right? We can simply write the algorithm, but I will give you the C code for it, and you can of course convert it into an algorithm and write it back in case you feel it is easier for you to remember. The concept here is that you will have to you'll have to find the minimum. For the minimum element, you have to go far left as possible in a binary search tree, because you know binary search tree in order traversal start from left. So the least element will be at the left, the highest element will be at the right. Go to the left, you'll get the minimum element. Go to the right, you'll get the maximum element. So that is what is the concept of a minimum and maximum element on the binary search tree. Now suppose that you have the standard structure of the binary tree or a binary search tree for that matter, and the standard structure of this particular of any binary tree is what? We know that it will have a struct node, right? So and then it will have the int data inside that, and then we will have the struct node left and right, the left and right pointers, which is also going to be struct node. Sorry, the pointer is here, right? Struct node is the data type, and we will say we have a left pointer and we will say we have a right pointer, right? So this is what we will say, and I think that's all that we need to put in the structure, right? So that's there. Now if I say int find minimum as my minimum finding function, then all I need to do is I need to pass it the root so that it can start from the root in order to find the minimum. So we will say struct node start root so that it starts searching from the root to find the minimum value. Now if the root is null, we will do a customary checking. If the root is null, then we will say that your tree is empty. We will say tree is empty, right? So this is what we will say if the tree is if the root is null, and of course we'll have to return a invalid index so that the caller knows something went wrong. Close the brackets. Now left, right. Why? How do you go left? We will say while root left is not null. So we'll keep on moving the left to the root left. We'll keep on moving the root to the root left. This way we will keep on changing the root, next root to the root left, next root to the root left. So it will go on moving left. And then when we have reached the end, we will, therefore my root left is null. So therefore we will return the root's data. That is my minimum element. Let's take an example. So let's say I have 40, 10, 30, 60, right? So I have created it like this: 40, 10, 30 is going to be less and then greater than 10, and then 60 is going to be greater than this, right? So if I take one more element just to show the right side of it, so that we can appreciate what is happening, so we will say let's say 75, and let us take one more element to the left, which is 5. So we will say this is 5, right? So this is how I conceive this tree or envisage this tree. And when we are talking about this tree, let us see how this algorithm behaves. So if I pass this root, then the root is not equal to null, right? So the root is not equal to null. I've passed this root, the root is not equal to null, so this code does not fire. Now root left for this, the root left for this is 10, right? It is not null. then make the root equal to root left. So now the new root becomes 10. Then the root left for that is also not null. Then make the new root as 5. Then the root left for that root is null. So then print this as the smallest element. Print this as the smallest element. Return root.data means return this. So that is how it will be. Now the right is just the reverse. I'm not writing it. I'm sure you can understand. The same thing will be written. Only thing is here instead of left it will become a right. Right. So that's all it will become. Instead of left it will become right. And instead of this left it will become right. That's all. These are the only two changes that you need to do. Right. So we will say that okay, we got a root. The root is not null. If it was null it will do this. Now we will go right. So root right is not equal to null. Root right is not equal to null. So then 60 becomes my new root. 60 becomes my new root right. So root right is 60. So my current root which was at 40 becomes whatever is this root right. So the current root becomes 60. Right. And then we do the same thing, that this is not null. So the current root which was pointing at 60 becomes the root right. So the current root now becomes 75. Right. The current root becomes 75. Again the root right of the current root is null. So print this, return this, and that is your highest element. So 75 is your highest element, 5 is your lowest element. Because it is a binary search tree, it supports in-order traversal as an ascending order. The leftmost element will be the minimum element, rightmost element will be the maximum element. And that's how we solve this problem. The value of a binary search tree can be sorted in ascending order using which traversal? We have discussed that using the in-order traversal. If you do an in-order traversal, you will get the sorted order of the binary search tree. All binary search trees are binary trees, but all binary trees are not binary search trees. We have already discussed this. What is the worst case time complexity to access or search an element in a binary search tree? Now the worst case is actually order of n, because we have drawn the skewed binary search tree, right, where we will see that the last element is this search element, then we'll have to take order of n. We have also discussed this question. So I think that's all that I had in store for this particular session on binary search tree and the threaded binary tree. And I hope you can understand why these are necessary, why these are essential, and what advantages it brings to the table. In the next lecture, we'll complete the sessions relevant to the other topics on trees, particularly B tree and B plus tree, and the AVL tree, of course. And that would complete the things that we wanted to do on trees. So till the time we meet next, happy reading, happy learning, and take care. Thank you so much.